component for aftermarket automotive components. We are giving this to, I think, to in Europe somewhere, and so we were originally making this out of gravity casting and machining a lot of the sections later. There's a bearing section in the center that we had to machine. Obviously, this whole thing was being through CNC turning and everything. There's a significant amount of machining to cut down the additional added allowances that were added during the gravity casting process. But after moving it to high pressure die casting, we were able to reduce the cost. Obviously, we get a net finish, so there's no other machining apart from the bearing machining in the center and the holes. The holes are always done later. So, and there's increased production. So earlier, for doing about 200 units, it might have taken us maybe 3 months to do. And we would have taken 3 months time, figured out how to schedule and do all of that. But now this can be produced in just 3 weeks, 4 weeks. The whole quantity is finished, and we dispatch it. So with the machining included. So there's significant increase in production capability and also increased strength, because gravity castings and sand castings are weaker than a pressurized metal being casted. So high pressure die casting definitely has significantly higher properties. This is the third example. This is for a rugged tablet that we make for defense customers, and they were doing sand castings and machining, and that was suitable for maybe about 50 units. When they were prototyping, they got 50 units, and they were considering doing the same way. They didn't know how big their orders are going to be. The second it reached 250, they realized that no, we are spending too much time in machining, and then we recommended that why don't you just switch to high pressure die casting. It's a higher die cost initially, which is paid off very quickly for their part. So that significantly reduced the cost, of immediate reduction in cost for them. Obviously increased production capability, increased strength because of transition from sand casting to high pressure die casting. And the last thing that they were able to use is the thinner walls. So when we were doing sand castings, we needed at least 3 mm to maintain 3 mm thickness throughout, or 4 mm thickness throughout. But when you're moving to high pressure die casting, you have higher strength, and you can cast really thin walls with high pressure die casting. At least in magnesium, you can. With aluminum, there are standards of 1.5 mm, 2 mm sometimes. But with magnesium, you can do 1 mm, you can do, we've also done 0.7 mm wall thicknesses. So you get significant stiffness and strength in that. So we were able to reduce their wall thickness to 1.5 mm. They were happy with that. It meets the rugged standard as well. So that's another example of optimization as well. So you have an existing component. What are the things that you have to do to your part to make it suitable for high pressure die casting? These are some of those things. So removing undercuts, adding ribs, adding radiuses and fillets, optimizing your design for excess material, draft angles, and then engraving and embossing. I'll show what this is. These are all die release considerations. So, and this is just an image to illustrate what this means. These are the two sections of the fixed and the moving side of the die. This is for draft angle. So you need a draft on both sides of the die so that the part comes out and does not get stuck within the die. So this draft is not much, which is about 0.5 to 2 degree draft that is required to come out of the die. So it's all depends on the size of the component. The larger the size, the more draft we would request. But yeah, so that's something that you have to add into your components and all features which are touching the die. So that's one. The second is radii and fillets. So sharp corners cannot be achieved in high pressure die casting. So we would discuss with your team to make sure that you are adding radiuses on the outside and fillets on the inside. And this is not only increases the strength of the component, it also is better for metal flow and metal flow as well. So this is something that you would have to add for all sharp corners that you might have. Maybe in machining you were doing sharp corners, or even in machining you would expect a little bit of radius, but in this for sure you need a good amount of radius to do high pressure die casting. If according to your use case anywhere sharp corners are required, what do you do then? We have secondary processes to help you with that, sparking being one of them. So we can do a secondary operation to create a sharp edge wherever you need for fitment, form, function, whatever that might be. So we can do that at a later point. But as cast part will not have any kind of sharp edge. Undercuts. So removing any features which have undercuts. So this is just an example where you see the orange component. There's one feature in this casting which is going inside the die. So even though the top die comes out, the bottom is stuck because of this one feature. Now there's a lot of ways of even creating this feature in high pressure die casting. There's a lot of ways of solving this problem. You could change the orientation of the part. You could change the parting line. So the line over here that is separating the dies, this line is called the parting line. So you can do a little bit of, like try and be innovative with the parting line. You can change the orientation of the part. You can also, the most commonly done thing is adding another piece of the die, not just the top and bottom, but a side uh, tooling as well. So something that moves sideways, and that would have a few features from this side. So in those ways you can solve all these issues as well, but we would have that discussion in detail with your team to understand, is this feature absolutely required, or can we eliminate that feature, or change the orientation of that feature to uh, you know assist with the die release, things like that. Because every time you add a side core, it also increases complexity of die construction. It might also increase the cost of production, and therefore the part price slightly, very slightly, but that is something, if we can avoid, you should avoid. Optimizing design. So here's an example where we have a die cast part. This is without creating like weight savers. Here you've removed a lot of metal, and you have created like a pocket, and this would have a similar, this will do the same function as this, but and a third version where you optimized it further to have more ribs and more holes as well. So kind of when you're optimizing design, you can also add, I can give you a lot more examples if if I had my files, if I could show you specific files, but probably we have this discussion with the customers file as well, that where can you add or remove excess material. So removing excess material where possible, using something like a pockets and stuff like that, and also reducing wall thicknesses. So when you were doing the same component using machining, or when with any kind of other casting process, you would have considered a certain kind of wall thickness, which can be further reduced already when you're going with high pressure die casting. So that's something to consider. So those kind of optimizations have to be done upfront. Ribs. I'm sure you guys also are aware what ribs are used for, to increase strength when you have thin walls. So without increasing the wall thickness, you can still maintain strength. So, but we would recommend that when you have thin parts, just add a rib to increase that strength, but only add a rib if it's absolutely needed, because ribs also add to the complexity of the design. And the last part is text in the component itself. So usually people do engraving, laser engraving or regular engraving, or embossing, not really, but that's something that is directly possible in the die itself for high pressure die casting. So you can get any kind of text written on the part, and not as a secondary operation, right? So that can reduce slightly. There's a reduction in an additional reduction in secondary process, and that's also one more thing you can keep in mind. These are just a few. uh, I'm sure when I'm looking at individual components of customers, there's a lot of specific things that we would tell you about die release, where it's a challenging thing and what else. But these are the general major ones that to consider. In terms of metals that can be die casted, I already mentioned zinc, aluminium, and magnesium. So we'll just take you through the die casting versions of that. So magnesium to begin with, this is a not commonly used in India. It's just making a late entry in India. We've seen a lot of electric vehicles, drones, and satellite programs and defense programs have been using this for forever now. But industrial equipment and new age industries like robotics, these people are starting to use magnesium very extensively, and the more um, they're starting to use magnesium significantly more. And why it is used, it's the lightest structural metal on the planet. It's anybody who's trying to lightweight their product in today's day and age, there's no reason why you're not using magnesium. It's used as a replacement for aluminum, steel, plastics, and titanium. When you're doing it, replacing magnesium with a steel or a titanium component, you just have to increase thicknesses to kind of meet the same kind of factor of safety. Reduce thicknesses when it comes to plastics, and you can use the exact same design. If it's an aluminum component, you can use the exact same design for magnesium. So that's something you should know. In terms of damping properties, so magnesium has excellent damping coefficient. So it is crack resistant, impact resistant metal, and it has 20